Hi guys, how are you doing? I've just woken up and I have to say the weather today, oh, it's really freezing guys. I'm literally wearing two jerseys right now. But I have a stuff I have to do. I have a lot of stuff I have to do today, so I had to wake up earlier. It's literally around 10 a.m. I'd actually set up my alarm for 11 a.m. but 10, that's good, right? So that being said, the weather of today just gave me an idea of a project I once worked on, which was a PID temperature control system using Simulink, right? So I modeled a heater, temperature variation of the heater, the room. You know what? Let me pull up the Simulink module real quick. So if you're having trouble modeling differential equations in Simulink, then this video is for you. See you. What's up you guys? So today I'm going to show you the PID temperature controller for the house I was talking about, and also show you how to model differential equations the easy way in Simulink, right? So as you can see, we have many blocks right here. So let me press spacebar. Okay, so spacebar is for zooming the modules. So you can see they became bigger. Yeah. Okay, so on my screen now we have many blocks, right? We have the scope block to measure the room temperature. We have the warm, we have the heater. So if you're wondering how I put these pictures, it's just mask, right? So if you double click on the block, on the subsystem block, like right click. Okay, computer is quite slow, but okay. You see right here where it's written mask, and you create edit icon image, right? And you browse location of the image you want to select, right? Okay, so we have the heater and the warm. Let me open the heater first. So that's the differential equation of the heater, right? And we have the warm, and we have the warm. So right now the equations are appearing a little jumbled, so that's why I want to show you how to model a differential equation. So for example, we are going to be using a simple differential equation, right? Let me try to increase the font size of this. Okay, hope you can see. Yeah. So dy dx, okay, let me check the equation I want. Dy dx equal to 5x. No, dy dx plus 5x plus 3 equal to 0. Okay, there we have our differential equation, guys. So how do we go about it? Okay, first things first, you need to group your items, right? The differential terms on one side and the other items on the other end, right? So how do we go about it? That means dy dx is now equal to what? Minus 5x minus 3, right? We've done the hard stuff, guys. So now let's model our terms. We begin with the left side, right? So the left side is dy dx, right? So how do we get dy dx? Okay, we get dy dx by integrating d squared y dx, d squared y dx squared, but that's not what we are looking for, right? I'm just joking, right? So here's what we do. We get dy dx by differentiating y, right? and we get y by integrating dy dx, right? So you pull up your integrator block, right? Then if I extend this, right, so extend this, I don't want to complete. If I name this line as dy dx, my font size is it? How can I increase the font size of this? Okay, I hope it's visible, guys. Okay, let me put an annotation right here. So this is dy dx, right? Now let me increase the font size first. Use 24. So this is dy dx, right? I said before. So this is dy dx. So if we integrate it, so that means I can cancel this, right? So if we integrate it, by the way, this is an integrator block, right? So if we integrate dy dx, what do we get? Yes, get y. So let's put our y here, font size 24. Okay, now what? Let's click here, move it down. Yeah, we get y. We have modeled the what? The left hand side. So now we want to model the right hand side, right? So a -3 block in -5x, right? -5 times x, you can actually use the gain to multiply the x. So x will be a constant, right? Okay, let's just say it's x, right? Okay, and we have a gain of what? -5, right? Okay, so it's -5x -3, right? So we create a constant block, label it -3, right? And what's the overall operation sign? Okay, so that means we now use an addition sign, right? So that it becomes -5 x plus -3, right? So where is this going, right? According to our equation, it's going to what? To the dy dx, right? Like this. There you have it, guys. Let me try to move this. There you have it, guys. Isn't it nice? So for the y, I guess we can use a scope block to visualize the output. There you have it. Okay, so now you have solved the equation, right? So how do you visualize the answers, right? So we have to set an initial value for our integral. Let's say it's 20. I don't know what kind of equation you are solving. So, okay, we have set our initial condition as 20, right? Then for our x value, okay, so for x value, I think let's use a sign block to see how that will change, right? Let me delete this. This amplitude 1 0. Okay, let our x change from 1 to 2. Okay, so let's the output now. Just press run, right? You see the scope, sorry, and the scope. That's the result for our y. I do not know why it's appearing like that. Is it because of the solver? Like, I mean, the output of the graph, it's not that smooth, right? Let's try to see how this. Sorry, can just click here, right click. Let's see how the sine wave is coming out. Yes, because of the solver. You know, that's for another video, don't mind it right now. Okay, so we are done with this example, right? So now we want to model something more realistic. So we want to model this second order differential equation for a pendulum, right? So let me write it first, but let's delete this one, right? Some of this one here. Okay, so it's d squared d theta plus g over L sine theta equal to 0. Okay, so first things first, we'll group the items, right? So d squared d theta goes on one side, right? The other terms become minus g over L sine theta, right? Okay, so let's model the left hand side first. So our integrator block as usual, right? But this time we are starting with what? I want to put block name. Where is your block name? Okay, so D. Use annotation so you guys can see. So d squared d theta, right? if we integrate it, it becomes use another annotation. It becomes, sorry, it's d squared theta dt squared, yeah. Sorry guys, d squared theta dt squared. dt squared. Okay. Let me leave this side. So this side becomes extend becomes d theta dt, right? So you have to apply another integral block. This becomes theta, right? We are done with the left hand side. So now how do we model the right hand side? Simple. Okay, so minus g over L, these are constants. Sorry, constant 1, 2 becomes L becomes theta. Okay, actually, as you can see, theta is already here. As I was saying, theta is already here, so let's delete this. However, we want to use a MATLAB function that takes in theta and outputs sine theta, right? Let's wait while it's loading. There we have it, right? This to run. Okay. If you haven't used MATLAB functions, don't worry again, that's not the point of this video. So we get our theta and it goes into this function and outputs y, and y is our what? Is our sine theta, right? And we have our L. So now we need another g, so let's put another constant, but we want it to be g. Okay, so as you can see, it's outputting an error because I haven't defined these constants in MATLAB, right? So it's g over L, right? The minus sign. So either we can say minus g, right? Say minus g over L. Let's use a divide block. So minus g divided by L times sine theta. I need the product. There you have it. there. Okay, so now this is the output of the right hand side and this is the output of the left hand side. So what do we do now? Yes, connect them like this. There, we are done. So let's try to run this and see how it comes out. Oh, we have to define the constants. Okay, so you know what, let's leave this as 9.81. Let's leave our length as 2 meters. Okay, initial condition. Now I do not know what I'm doing, guys. Just guessing. Let's try to check if there aren't any errors. Here's one. So let's use a scope block to try to visualize our data, how our angle is changing. Okay, so let's check out the scope block for how the angle is varying. Oh, it came out nicely. So as you can see, our angle began at around 12 degrees, then we extended it further, then it went to the other side, came back like this. There isn't any damping, so it will move like this infinitely. An interesting approach to this example would be to model this system in Simscape. So Simscape, we are now using real physical blocks. Right? There'll actually be a ball attached to a string. Okay, anyway, that's our next video. So thank you. So you've reached the end of the video, guys. Don't forget to turn on notifications, subscribe and like. Peace.